All right, welcome to 10.1, sequence and series and sigma notation. This section is kind of like an overall intro section with some things you will need to gather in this section in order to do future sections. So this is important to at least get notation down and some of the right way to say certain things. Okay. So first part of this section is about sequences. And what's a sequence? An ordered list of numbers. I gave you an example here: 2, 5, 8, 11. Uh, we would call 2 the first term, 5 the second term, 8 the third term, and so on and so forth. I know it seems basic, but I need to say that in order for you to do some of the things in the future. And one of the ways we can solve for sequences or write a sequence in a certain way is called an explicit formula. And what this does is it gives the nth term a sub n as a function of n. Now, these equations and formulas are usually a sub n equals blah, okay? And we are able to write a sequence based off this formula, okay? That's why it's written like this. It's going to be a sub n equals something, okay? And we'll do some work with that here in a moment. So these two examples, we're not going to be finding the explicit formula, even though we could for these. We'll do that in a little bit. But I thought we'd start basing and say, find the next four terms in these sequences. So one of the things we could be doing is adding or subtracting a number, or multiplying or dividing by a number. Here we're going by 16, 8, 4. It's not going increasing by the same number. But what do you notice? You're dividing by 2 each time, right? So if we divide by 2 again, so 4 divided by 2 is going to be 2. Divided by 2 again, you get 1. You get 1 half. Divided by 2 again, 1 half. And then divided by 2 again, you get 1 fourth. Cool. So what's happening here? So we get this other one: 1, 2, 3, 4, 5, 6. So we're increasing each time. So you're adding one more each time. So if you're adding 6 here, we're going to be adding 7 the next time, and 8 next time, and 9, and 10. Boom. Now we got find the first four terms of the sequence given by a sub n equals n to the third minus 10. So if we put 1 in, okay, when we say first four terms, when n equals 1, that's the first term. So 1 cubed is 1, 1 minus 10 is negative 9. Second term is when we put 2 into the equation. 2 to the third is 8. 8 minus 10 is negative 2. 3. 3 to the third is 27. 27 minus 10 is 17. And then 4 into the equation. 4 to the third is 64. 64 minus 10 is 54. Here's your first four terms of the sequence. You will see the explicit formula more in the future as a way to write it, where we would find this equation based off a sequence in the next section. But for now, I just expect you to know what it is and how to find the first four terms, or to predict what the next four terms are. Next formula is called a recursive formula, and it's a recurrent relation is where it kind of gets its name from. It's a formula defining the nth term in the sequence. Uh, these formulas are somewhat can be similar in some ways and also different in some ways to what we see. This would be a sub n equals a sub n sometimes minus 1, and it'll be times a number or minus this number, etc. Meaning as one term increases, as your n value increases, what are you going to get? So if n's equal to 2, if we're looking for your second term, be a sub 2 equals a sub 2 minus 1. So if you know your first term, you know what's going to happen in here. And then you might be like times 2 minus 1 or whatever, okay? And you're able to work it out from there. And then you can Want to find the third term, going to be a sub 3 equals, etc., etc. 2 times the second term minus 1. That's going to keep happening over and over again. So we have two recursive formulas. We need to find the sixth term in each sequence. And luckily for you, I gave you the first term. How nice of me. So in order to find the second term, I'm going to rewrite that to a sub 2. A sub 2 would be equal to negative 2 times a sub 1. What's a sub 1? I gave it to you, it's 3. That's going to be equal to negative 6. A sub 3 is going to be equal to negative 2 times negative 6 equals 12. Next, throw in a sub 4. You make sure I have space. A sub 4, negative 2 times 12 is going to be negative 24. A sub 5, negative 2 times negative 24 is 48. A sub 6, negative 2 times 48 is negative 96. There we go. We got it. So that's the sixth term. See? We got 1, 2, 3, 4, 5, 6. There we did it. Next one. A sub 1 equals 8. Now for a sub 2, we got to do 2 times 8 minus 7, which is 9. A sub 3, 2 times 9 minus 7, which is going to be 18 minus 7, which is 11. A sub 4, 2 times 11 minus 7. That's 22 minus 7, which is 15. And then we're going to do a sub 5. 2 times 15 minus 7 is going to get us 23. E sub 6, 2 times 23 minus 7 equals 46 minus 7, which is 39. So the sixth term is going to be 39. Converging and diverging. So converging is sequence has a limit that such that the terms approach a unique number, and then diverge is sequence does not have a limit that approaches a unique number. So if we were to have a number term in your sequence, as that increases, it's getting closer to the same number, then it's going to converge. If it's not going to any specific number, just like increasing forever or decreasing forever, then it's diverging. All right, so let's try these two right here. As n increases right here, this one, let's say n is 1. N is 1 is going to be 32, right, for a sub 1. If I did, let's say, a sub 6, we are getting 6 would be, that's 64 divided by 12. I wish I picked a nicer number. It's 5.3, I believe. A sub 32 gets you 1. And then if I pick a really big number, you're going to get closer. It's going to get a big fraction. You're going to get closer and closer to which number? 0. So it's going to be convergent. It's converging to a number. What number is that? 0. Now this one, a sub n is equal to 3 times negative 1 to the power of n. So what is happening here? Well, if I put 1 in, you're going to get negative 3. A sub 2, you're going to put 2 in, you're going to get 3. A sub 3, you're going to get negative 3. You're going to keep going back and forth. It's not going to go to any specific value, so it's going to be divergent. There we go. So we got some definitions about series. Series is another way to write our sequences, pretty much. The only thing included is that we're going to add up all those numbers together. So series is to indicate sum of all the terms in a sequence. Okay. Finite series is sum of all the terms in a finite sequence. Infinite series is sum of all the terms in an infinite sequence. Typically, and we're going to show you this here, we write these in what we call sigma notation. A finite series will have a number up top right here. Okay, not necessarily 0, but there'll be a number. As opposed to an infinite series, well, you'll see the infinity symbol right there. That would be infinite series. And before we do any problems with series, we're going to talk about partial sums. Okay, partial sums would be going from pretty much the very beginning at a equal to 1 and adding all the values up to whatever value you're asking for. In this case, it's the sixth partial sum. So we have a sub 1 equal to 8. A sub 2, we have our formula over here where we can put in a sub 1. So it'd be 0.5 times 8, which is 4. A sub 3. 0.5 times 4, which is 2. A sub 4. 0.5 times 2, which is 1. A sub 5. 0.5 times 1, which is 0.5. And a sub 6. 0.5 times 0.5, which is 0.25. If you add all those together, you will get 15.75. All right, and then for the down here we have the seventh partial sum. If I put 1 into this, 1 to the 1 over 10. 1 over 10 to the 1 power is going to be 1 over 10, so we're going to get 3 over 10. A sub 2, put 2 in, you're going to get 1 over 100 times 3, which is 3 over 100. Oh, nice, I'm just going to keep adding zeros here. A sub 4, we'll get this 3 over 10,000. A sub 5, 3 over 100,000. A sub 6, 3 over 1 million. So, if we add all those together, you'll get 0.33333333. All right. And this is sigma notation. Now, when I give you a problem, it's going to be simply that. But what you're going to be doing is plugging in whatever this number is right here, in this case 1, and going all the way to k. All right. N is what we call the index of summation. And k is the upper bound of the summation. Upper bound of the summation. And 1 is the lower bound of summation. As I said, we go from 1 all the way to whatever that k value is. So I have 3 examples here. Find each sum. So if I put 1 into this, I'll get 1 squared is 1, 1 minus 1 is 0. Oh, nice. So when I put 1 in, I get 0. When I put 2 in, 2 squared minus 1 over 2, that will get me 3 halves. I'm low in space here. I wish I had more space. 3 squared minus 1 over 2 will get me 4. 4 squared minus 1 over 2 will get me 15 over 2. And then 5 squared minus 1 over 2 will get me 12. So therefore, if I add all those up, I'll get 25. Next, we got, I'll use a different color so you know how this is different. Here we got 7 to the third minus 7 squared plus 8 to the third minus 8 squared plus 9 to the third minus 9 squared plus 10 to the third minus 10 squared plus 11 to the third minus 11 squared plus 12 to the third minus 12 squared plus 13 to the third minus 13 squared. And what does that add up to? Then you calculate, you'll get 7,112. Finally, this is an infinite one, okay, so it goes on forever. So you'll start to notice that it's going to get closer and closer to a certain value as it keeps going on forever. So let's figure out what that would be. So we'll put 1 in, you'll get 6 over 10. 2 in, 6 over 100. 3 in, you'll get 6 over 1,000. 4 in, 6 over 10,000. 5 in, 6 over 100,000. 6 in, 6 over 1 million, and it's going to keep going on forever, right? You don't want me to scroll up. So what do you get when you add them all up? You're going to get closer and closer to the same value. That value is 2 over 3. That's going to be 0.6 repeating forever. So you should know that that fraction is in fact 2 over 3. All right, appreciate you watching. I'll see you in class. Bye-bye now.